transformers. So now we get into the last part of the chapter's electromagnetic application, and the last application, the first application was transformer, and now the second one is generators and motors. So generators and motors, in a more proper term, it is usually is called as electrical machines, right? So it is usually called as electrical machines. And as a function of the mode of operation, it can either be called as generator and motor. And we'll see later how does an electrical machine becomes a generator, and how does it then becomes a motor. But now for this section of generators and motors, or electrical machines, what we're going to see is four things. So the first one, we're going to look at the basic electromagnetic theories, right? Basic electromagnetic principle that is applied to make a motor works, right? So we look at a few, it might be somehow revisions towards what we have seen earlier. Some other rules will also be introduced to tackle the all the basic that you need to know that makes an electrical machine works, right? And then in second part, what we're going to learn is we're going to learn about the construction. So the topology is going to be a one simple topology of a DC machine, DC motors, the construction of it, and the usage mode. So what I mean by usage mode is basically this two mode, either in generator or motor. And then in third part, we're going to look at more specifically into the components of a DC motor, the components of DC motor, and how do they works, how does they contribute into the working of a DC motor for each components. And then at the end, finally, we'll look into several characteristics that is important to motors. So several characteristics of a DC motors again. So basically, in terms of motors, in terms of electrical machine, be it generator or motors, there are plenty types of machines, of motors. But for the purpose of introduction in this subject, we're going to look only at DC motors, right? So we're going to look at in the final part several characteristics of DC motors, which may include also the efficiency of a motors, right? So let's start with the basic electromagnetic characteristic. So now again we go to Faraday's effect. So basically what happened here is, imagine if you have a magnetic field, so that could be created by a permanent magnet. So here basically the figure shows a permanent magnet, but by now you know that magnetic field can also be created by an electromagnet. If you have a magnetic field, and then if you have a copper wire inside that magnetic field, and if you generate motion, if you put motion onto the copper wire that is placed inside the magnetic field, what you will create is basically you create electricity. There will be current flowing inside the copper wire. By now I think you understand what's happening here. Basically what's happening is there is a constant magnetic field across the wire, and when you move the wire using your mechanical motion, what happens is basically your conductors, your wire, are seeing the variation of flux. As it moves, it sees variation of flux. It sees dphi over dt. And we know that Faraday says if you have dphi over dt, then we create an electromotive force, EMF, which is a kind of voltage. So you create electricity. So this Faraday effect, basically it represents the mode of generators. You have magnets, magnetic field, copper wire, a moving copper wire or conductors, then you create electricity. What about motors? Motors is basically the other way around. When you have magnetic field, when you have copper wire, but instead of introducing a motion, what you have is electricity that where you have currents that goes through your copper wire. So copper wire, a current that goes through it inside a magnetic field will create a motion. So it's just the interchangeability between motion and electricity, right? So if you have motion, then you create electricity, but you have electricity, then you create motion. So the basic concept, again, just for revision, voltage is written as V, is the potential to move the charge in volts. It's the potential difference, right? Current is written in I, is the charge movement or the flow rate of the charges. So it's dq over dt is the flow rate of the charge movement. And then you have resistance R, which is can be basically, which represents the difficulty of current to go through conductors. So the relation between V, I and R is written here. So V equals to Ri, where we have R in ohms. And then power, if you want to calculate powers for a DC current, power will be equals to I multiplied by V, or I square multiplied by R. Both of them are the same thing. So this is the basic principle that we're going to be using. So now we'll see what will happen when we have um, a current carrying conductor placed inside a magnetic field. So imagine you have a permanent field, a constant field that can be created by two poles of permanent magnets, or can be created by an electromagnet. And then what we'll do is we'll place a conductor. So this is a conductor that conducts a certain value of current. So the conductor with a certain value of currents, we know that it will create a magnetic field around it. So this is the field due to the current in the conductor. This is just the right hand rules, the basic right hand rules. When we have this, what will happen is we'll see here, basically the two magnetic field will interact with each other. So you have a magnetic field from the permanent field, and you have the magnetic field that come from your conductor, and both of them, they interact to create a certain force, right? So when you have conductors that have currents conducted in it that create its own magnetic field, placed inside an area where there's already a permanent magnetic field, what will happen is it will create force in a certain direction. So which direction is that? So if you want to know which direction is that, what we have to look at is there is basically a rules for this. That's what we call the left hand rules, the first left hand rules, where we have an indication of which direction will be the thrust or the force when we have currents conducted in a conductor placed inside the field. So now what it represents is, if I can show with a pen, we have a three axis parameters. Let's say I'll call this one as X, Y, and Z. So the X represents, or your second fingers represent, the currents that circulates in your conductors, while we represent the permanent field. And then if you have both current placed in a permanent field, what we create is basically you create a thrust or a force in this direction, right? So it's the same thing that's being presented here. Imagine you have a conductor that conducts current in direction X, and it is placed in a magnetic field that follows a certain direction Y. You create a force in the direction Z, right? So how do we quantify this force, the value of this force? Well, the value of this force can be quantified by this particular equation. So the force created in a current carrying conductor placed in a magnetic field equals to B multiplied by I multiplied by L multiplied by sinus theta. Okay, what is B, I, L, and sinus theta? So the first one, B, is, as you can imagine, B is basically the magnetic field, right? The value of the magnetic field in, of course, B is in Tesla, so this B. And then I is the length of the conductor. So basically it's this length. So the length of the conductor that is placed in the magnetic field. And then no, that's L, I'm sorry, that's L. And I, what's the I think you can also imagine this, that I is basically the current in amps. So it's the current that circulates in that length of conductors. And sinus theta, okay, now we have sinus theta. We'll have force F at its maximum value if our current I is perpendicular to the direction of magnetic field, right? It is at maximum. But if you put it, if we look at here, if it is perpendicular, if the current circulating in the conductor is perpendicular to the magnetic field, then we'll have force equals to F max. But if by any chance you rotate your conductors into this direction, where you have your current in parallel with your magnetic field, you have a force 0. So in between the position of vertical, perpendicular and parallel, the force actually varies from maximum to minimum. So that variation is being represented by sinus theta. So theta represents the angle between, so it's the angle between the magnetic field and the direction of current. Right? So this equation is very important. It shows us the magnitude of force that's created by on the conductors that carries a current I, where the conductors have the length L and is placed in a magnetic field with intensity B. So if their direction has an angle of theta, then the force will be F BIL equals to BIL multiplied by sinus theta. Right? Okay, now that was for a single coil. What happened if we have a multi-turn of coil? So just now we didn't have single coil. Just now what we have is a single wire with a current conducted in that single wire. But now what happened if we have, instead of having a wire, we have basically a coil. So a multi-turns coil, just like a solenoid, right? So the current is circulating in this coil. So if we have coil, basically it's not force anymore that we'll create. We will create a certain level of torque. And the equation resembles to the one that we had just now, which is B multiplied by I multiplied by L sinus theta. But now instead of a BIL sinus theta, if we have a coil, then it will be equals to K multiplied by B. So it's the same B multiplied by I omega multiplied by sinus alpha. So what is B? B again is a magnetic field, magnetic flux density in Tesla. K, okay, now K is a constant that depends on the coil geometry. So it depends on how many turns do you have, on the on how large is the coil, how long is the coil, and so on and so forth. Right? And then IW is, as you can imagine, IW is the current that circulates in that coil in amps again. And alpha is just like the previous equation. Alpha is just like theta, is the angle between the magnetic field and the normal to the plane of the coil. So what is normal to the plane of the coil? So imagine if you have a coil like this, a surface coil like this. So normal is that direction tangent to that surface of coil, right? So it's the angle between this direction and the magnetic field. Okay, now let's look at an example. So imagine if we have now a permanent magnetic field. So we have a north pole in this side, south pole in this side. So what we have is basically you have a magnetic field, permanent magnetic field in this direction. And then what we have here is basically in yellow. In yellow is a coil, right? In yellow here, what we have is a coil that conducts a certain current. So the coil is basically connected to a power supply, and the power supply, so this is a component that I'll explain later. So there's a current that circulates in this coil in this direction. So if you look at portion by portion, what happened is here you have a current just like inside a straight wire that we've seen in previous slide. And we also have a magnetic field perpendicular to the direction of current. So naturally, if we look into the left hand rules, it will create a force that push this portion of this portion of the coil to downwards to the bottom, right? And if you look at the portion on the left, the currents now circulate in the opposite direction. It comes from the paper, inside the paper, towards our direction, right? So if we have this direction of current and still maintains the same direction of magnetic field, then we would create a force that goes upwards, right? So one on the left upwards, on the right downwards. It means it creates a rotation with the direction of clockwise rotation, right? So this clockwise rotation is what this clockwise rotation with force F on left and right hand side is basically being represented as torque here, right? As this torque here. So what happens is that the coil will rotate and rotate until it becomes in this particular position, and then it can continues to rotate. Of course, we'll see later the operating and the how it functions. So basically, this is how this is the basic principle on how do we create a motor. This is the basic principle of how does a motor works in motor modes, right? So now let's see at the parts of a motor. So the first one is what we call an armature or rotor. Armature is basically is what being presented as rotor coils in this part. Armature is the part where you have what we've seen just now, the coil conducting the coil that conducts current that will rotate inside the motor. So that's what we call armature or rotor. And then the second component is what we call commutator. So the commutator is basically this segment in on the shaft that links between that's connected basically to the armature or to the rotor coils. So what's the function of this commutator? In order to be able to explain the function of this commutator, I need to introduce the other component, which is brushes. So brushes is a component that is over here that we can see here on both sides. So brushes is basically the component that conducts electricity from the power supply. So imagine the brushes is basically you have two sides. The two terminals of the brushes will be connected to the terminals of your power supply. Imagine if it could be a battery or it could be a power supply. DC, in this case DC, because this is a DC motors. So brushes conducts electricity from the static. So basically we have power supply or battery that's not moving. What we need to do is to transmit that energy, that power, that current from a non-moving object into a moving a rotating shaft. So brush is basically made of a material that is that could support friction. So by friction, it transmit currents into commutators. So commutators is also a component that sometimes we call as collector, as it collects current from the brushes and send that current into rotor's coil. So then the rotors will have the rotor's coil or the armature will have current circulating in it and reacting to the magnetic field created by the stator magnets. So the whole rotor coils, commutator or collector are mounted on the shaft that is rotating, and of course the shaft later will be mounted in some sort of bearings. And then the next important thing, which is the stator magnets, or we can also call it a field magnet. So it's the component that provide that constant permanent magnetic flux inside the motor that will interact with the armature, producing this rotation, right? And then of course we should have a DC power supply that will provide provide power to the brushes to be transmitted into the commutator. Okay, now that we have seen the components and parts, we also know that an electrical machine, so we call in general a motor as electrical machine. Usually we call it a machine, but we call it as motor. But motor is really a mode of operation. The name, the usual, the correct name is electrical machine, but an electrical machine can be used as in two modes, either be it in motor or in generator. So the thing that we've seen until now is the thing that we've seen in previous slide is when we provide electrical energy, we provide current or certain voltage here to the brushes, and then it will provide at the output of the machine, it will provide a certain mechanical output which consists of torque and rotational speed, right? So here we have torque of the machine T, rotational speed of the machine omega m, and here TL is representing the load torque that comes from your application. So if you put in input an electrical energy and you produce at the output mechanical energy, that's what we call an electrical machine that is functioning in motor mode, right? And then we can also use an electrical machine functioning as generator mode. So basically they are the same machine, the exact same machine. It's just now instead of giving it an electrical energy, we'll provide to it a mechanical energy. It means we put it as input mechanical energy. We will rotate the shaft. What happens if you rotate the shaft? When you rotate the shaft, the machine will function as generator and will provide electrical energy in its output. So this is basically what you're seeing generally in a generator or an alternator. That's basically what it is. It's an electrical machine functioning as a generator. So for example, in Pasar Malam's generator set, gen set, what you have is the rotation will be provided by a small engine, and the engine is rotating the shaft, and the shaft of the motor will rotate the armature inside the motor and interacting with the magnetic field from the stator will produce a certain output of electrical current, right? So that's two mode of operation of electrical machine, in motor and generator. So now we comes to the part where now we know how how an electrical machines work. It can be in motors, in generators. We know all the components. So the next thing that will be interesting to look at is the characteristic of a motors. So again, now we are only limiting the study case to DC motors, because it's basically the easiest motors to be understood in terms of its principle, usage of principle in electromagnetism. So now the first characteristic that we can look at is the characteristic of torque and speed. So basically, when we supply current and voltages to the motors, the thing that will be useful in mechanical output is torque and speed, right? So how does a DC motor behave in terms of torque or speed? So here what we can see is basically the graph shows a torque and speed curve of a typical DC motor, right? It shows a torque and speed of a typical DC motor. So in y-axis you have the torque, in x-axis you have the rotational speed. So this line is basically the line of the behavior of the motor if you supply it with a constant voltage. So imagine if you give it a certain voltage V, then the motor will move along these operating points. For example, if you have so there's two interesting points, what we call no load speed and a stall torque. So how does this work? Imagine if you give 5 volts, imagine 5 volts to the machine, and if you don't have any load connected to the shaft, means it's not rotating anything, the motor will rotate at the no load speed, right? It will rotate at no load speed. But as you add load to the shaft of the motor won't be able to rotate at this maximum speed anymore. So no load speed is also the maximum speed. As you add load, then it means your motor have to provide torque to counter that load. Then what happen is your operating point of the motors will travel across this line. So for example, if you have a torque at this level, then the operating point will be here. It means your speed now have dropped into this level of speed to be able to pull this level of load, torque load. And then as you increase the load, imagine if you breaking the motors, or you're putting a lot more weight onto the shaft, what will happen is the point or operating point will move. So the speed will reduce, but it's carrying a lot of torque, a lot of load. if you continue to add load, what will happen is it will reach the point of stall torque. So what is the point of stall torque? The point of stall torque is basically the maximum torque that it can bear before it goes into zero speed. So it's basically the maximum torque before it goes into stop and not rotating anymore. But remember, this line is only for one voltage. If you change the voltage, then we have different lines. So for example, another voltage will give another lines of operating points, a higher voltage will give another higher lines of operating points that will give another maximum speed or another no load speed, and will also give another maximum torque or another stall torque. But of course, the maximum voltage will depend on the construction of the motor as well, right? Some motors can only support only until a certain level of voltage. So that's for torque and speed characteristic of a DC motor. So this is exactly what I've been explaining just now. So imagine if let me get a pointer. So if you have a lower speed, then you could pull. If you want to pull a lot of load, a lot of torque, then you have to sacrifice in terms of speed, right? And in the middle, basically, it's the product of speed by torque. So it's basically the power. So you're consuming this amount of power, and if you position in the position where the area is the maximum, so basically this is when the area is maximum, you're consuming the maximum power, right? You're consuming the maximum power in this condition. But if you go into higher speed, it means you cannot carry a lot of load anymore, you cannot provide a lot of torque, so now the power is also lower, right? And the last one is the relation between torque, power, and speed. So basically, we could have the constructor of a motor. For example, here is a sample of a Maxon motor. Could give us this kind of graph in their data sheet. So what does this graph represent? It represents basically in function of angular speed, you can only have a certain level of torque and a certain level of power. So for example, if we are at 100 RPM, and if you want to carry at this voltage, we can only carry close to 0.3 Newton meters of torque, and this is basically the level of power that we will have. So the power is basically at around a bit less than 3 watts, right? So this is a very small motors. It's just up to 5 or 6 watts, right? So where do we have the maximum power? The maximum power is consumed when you are around the middles. So you have half of this, you're using half of the speed to pull half of the maximum load. So this is basically what we've seen in previous slide, right? So the last thing that we need to consider as well is, of course, just like in a transformer, an electrical machine, motors and generators, both of them also have losses, right? So because inside them, they are basically just like a transformer. They have coils, and they have magnetic cores in the rotors, and they also have magnets, right, or electromagnets that will create the permanent field. So in terms of losses, they can have the same losses as the transformer. For example, electrical losses, they'll have copper losses, which is due to the currents that conducted in the circuits, in the coils. They can have also magnetic losses, which are iron losses and hysteresis losses, eddy current losses. So this is similar to what we have in transformers, but the one that we don't have in transformers, but we have in motors, is these two losses, which is mechanical losses and stray losses. So mechanical losses is losses due to the to the dynamic of the motor that's moving. So basically it could be because the rotor is mounted on a bearing, so there could be a bearing friction, windage friction, brush friction. You see, we transmit basically currents from the brush to commutator using friction, so there is loss of energy by friction and by heat as well, right? So, and the last one is a very small losses that we call stray losses. These are losses that can comes from the load as well. As you add more load, for example, there might be deflection of the shaft that add more to the mechanical load as well. So those are losses. If you look into a summary, for example, if we put a certain voltage and current into the DC motors, that will give us the power. So power is V multiplied by I. There will be losses across the machine, across the motors before it get into the rotational power, right? The mechanical rotating powers. So for example, there is a field copper losses for a motors that in the stator you have an electromagnets instead of permanent magnets. So you have what we call field losses, and then you will have brush contact losses, amateur losses. So brush contact and amateur is the transmission of the current from the non-rotating part to the rotating part. And then you have no load rotational losses and stray losses. So these are mechanical losses. So at the end you have a smaller amount of energy or power compared to the power that is put in input. So that represents basically the efficiency. That means you can calculate the efficiency, which is lower than of course than 100%, right? So here you have the efficiency represented by the Greek letter eta, is the mechanical power at the output divided by the electrical power. So how do you calculate the mechanical power? Mechanical power can be calculated as here, shown here, is the torque multiplied by omega. So just pay attention to the units. The torque should be in Newton meters and omega should be in radian per second. And what about the electrical input? So the electrical input, so power output over power input, power mechanical over power electrical. Power electrical is just simply the voltage multiplied by the current, right? So that's how we calculate the efficiency of a motor, right?